is this correct on A and B? Is this what you guys got? Josh didn't show me the work, but those you guys got though. 2 to the n minus 1. Yeah, maybe it's kind of easy to just see that because 4 and 64, nice powers of 2 and all that. There is another solution though. Do you even think of it? Yeah.
-2?
Yeah, it also an equals -2 to the n minus 1 is another completely valid solution here, isn't it? Just so you know. Yeah. What would the graph of this look like? Now, granted, this is nice. This is not a hard answer to give you because n we take to be integers. So, yay. It just alternates then, right? Looks like exponential over growth, but kind of like this, right? Right? Goes flying off. Right? What if n was an integer? A very good question. I mean, it's hard for me to even know, right? What is -2 to the pi power? Because that's going to be one of the values, right? That you're considering. Aren't you considering that? What is that? Is that even a positive number or a negative number? Do you know? I don't, off the top of my head, right? You can type it in your calculator, and it's one of the two, right? Maybe positive or negative. Or maybe it's not real, right? Like a lot of times we're going to get things that aren't real. Like if -2, we raise -2 to the 1/2 power, we know that that's not okay, right? Can't graph that. So we get some really crazy stuff happening here, right? Yeah, so we usually don't, I mean, usually when we're thinking about, so maybe this is where exponential functions differ from geometric. We said maybe yesterday that they're the same thing. They are, right? But usually when we think of exponential functions, there's a little asterisk that says, please do not let b the base of exponentiation. Please do not let that be a negative number ever. It's for this reason, right? We have like come into some really interesting prickly territory. Yeah. It's not that it's not interesting, it's just we usually don't talk about it in pre-calculus. Alright, so everyone okay with the warm-up? Very similar to what you did in the homework in one class session. Okay, what about the homework? Anything else you want to say about the homework? I'm trying to think if there's anything weird that happened in the homework. You took some limits, so you're good with those, and you took some you used some recursive rules, some of which were based on 2 initial conditions. Is that one okay for you? Yeah.
So it's not for like recursive, even like a sub n minus 1. What's the difference between like a sub and n plus 1?
Yeah. So sometimes the recursive rule, everyone understands what she says. I don't. There's someone like that in the homework. Yeah. So you can give a recursive rule in the following way too, right? Instead of saying a1 is 7 and an is equal to 52 minus a sub n minus 1 squared. Instead of giving it that way, you could give it instead as this, and this communicates the exact same information, right? So, except for this rule, you know, it's just off by 1 here, but the same rule, right? So if you want to know what A2 is, then isn't that, in this formula here, if you want to know what A2 is, that would mean in this formula, n is taking on the value 1, and that would tell you the same thing, that A2, if n is 1 in this formula, we're talking about A2 being 52 minus A1 squared. So it actually does communicate the same information. Yeah. Anything else on the homework that was? Had you add some stuff up at the end, right? So we haven't yet given you the formula. So it's good to make you add some stuff up by hand, or maybe some of you already cheated with the formula, you know it or something. We are going to talk about some quicker ways to add things up today. That's the goal today, is to talk about finite series. After break, we're going to spend a lot of time thinking about infinite series as well. So moving on now from section 9.4 to 9.5, right? Making progress. So I'd like you to be able to sum using some tricks, right, that we have, arithmetic and geometric series. And we'd also like to be able to use sigma notation or summation notation and play around with it and talk about some properties that we can use summation notation. You know, just basically kind of get our feet under us as far as sums go. And that is in fact what series means. So before I even launch into this, let's make sure we are clear. It's clear in my mind because I'm a math person, right? But to Anyone else who's not a mathematician, series, sequence, those mean the same thing, right? Sequence and series, those are the same thing. Like, there's a series of television shows or something, right? Like, that is not the mathematician's usage of the word series, though. When we say series, we like to hijack English words in math and make them more precise. So let me give you an example of a sequence first. A sequence would be like this: 1, 2, 3, 4, etc. And a series would be like this: 1. What's the difference? What's the difference? Yeah, there's a typographically there's a plus sign, right, instead. So, for instance, it makes sense for us to say evaluate the series, right? Because by series we mean synonymously sum. All right, so series means to a mathematician sum. All right, it doesn't make sense at all to say evaluate the sequence. What does that even mean, right? Evaluate a list of comma-separated numbers. What does that mean, right? But okay, so does it make sense? Yeah, Joshua. Yes, exactly. I didn't tell you how to do it yet, so maybe you just did it by hand. But you're going to have a quicker way to do it after today's lesson. Okay, so like I said, we need to lay the groundwork here. Let's talk about summation notation a little bit. It's obvious that I've already kind of somewhat assumed, haven't I, that you know a little bit about summation notation, that maybe you've seen it before, maybe you're exposed to it. At the very least, you know that the big capital sigma, which is what this big E looking thing is, it's not an E though, it's a sigma. You at the very least know that that like stands for sum, right? Sigma stands for sum. But maybe you haven't been real comfortable yet with all like the minute details. This over here, the little letter AK, right? In general, that's going to always be the explicit rule for your formula, right? You never put anything else there. Always the explicit rule for the sequence that we're going to be adding up. And then it's kind of like a little for loop or something, right? K is what I'm using right now, though you can use whatever letters you like in all these spots. K is my index variable. And we're letting the index variable take on the values between some beginning number and some ending number, K0, and in this particular case, N, right? So all these letters are upper gods. K0 is often 0, right? Or 1 is maybe even more often, right? 0 or 1, but it can be anything you like, right? You can start the sum anywhere you like. So for example, let's evaluate these sums. Again, let's be clear. The thing to the right of the sigma here, this thing here, this is the explicit rule, always, right? For some sequence that we're about to add up, okay? So what does this communicate? This says here, this first one, says let K, our index variable, be 1. Let it be 2. We always step up by 1, increments of 1. 1, 2, 3, 4, 5, and 6, please. Let it be those things. Plug all of those numbers into this formula, this explicit formula, and add up the results. Is that clear in our minds? That is to say, let K be 1. That would give us 2 times 1. Let K be 2. 2 times 2. Plus 2 times 3. Plus 2 times 4. Plus 2 times 5. Plus 2 times 6. All right. And what does that come out to be? You can just add it up by hand if you like, however you want to do it. The meaning of what? Yeah, sure.
How does it determine step?
Yeah, the step size is always 1. Yeah, and now there are ways you can hack the system, right? By making this a K over 2 or something like that, or making this, and then making this 12 or something. You can hack the system, but by default it is 1. There are ways of specifying it too, and this is not the only way that people use summation notation, but everyone would understand what we're saying here to mean step by 1. Yeah. So did everyone get 42? I heard some people say. Someone verify that, yeah. And then down here, notice my starting K0 value is K4, K equals 4, right? So I'm going to step through this, 4, 5, 6, and 7. Plug those numbers in to this formula, and then add the results, right? And that will be our sum. How many terms are in this expansion? Yeah, is it clear that it's 4? 7 minus 4 is, wait a second. 7 minus 4 is 3, and then plus 1. Is that always going to work? It's kind of the fence post error, right? So we're always off by 1 here. 7 minus 4 plus 1 gives you the number of terms. Does that work up here? 6 minus 1 is 5, plus 1 is 6. Yeah, there's 6 terms here. So let's just be clear. We're expecting 4 things here. Yeah, we do 4 squared plus 5 squared plus 6 squared plus 7 squared. Tell me what you get. All right, everyone's confirming that. And this could be a little annoying, couldn't it? I mean, this was not bad. But what if I did from 4 to 70? You know, you can imagine that would be a little bit time consuming. Right? You might have. Do you feel like a computer doing this? I mean, you kind of like are algorithmically sticking in, evaluating, adding. Right? That's what you're doing. You could easily have a computer do this for you. We also have some tricks that we're going to show you to evaluate more quickly. Maybe you have some formulas that add up the perfect squares or something like that. You know, people have developed some formulas for us. That's wonderful. The first one we're going to actually sum up later today using a special formula and show you that we can do this pretty quickly using a nice formula. The second one down here, there is a nice formula to add up the perfect squares from 4 to 70 or whatever you want. But we're not going to teach it to you today. Okay? You can go look it up on your own. All right, so you can play around with summation notation in expected ways. I think most of us would have the urge. How did anyone compute that 42, by the way? Did anyone do anything interesting? Did you actually do 6 times 1?
I just did 2 times what was this.
I would do the same thing, right? So that's my first property of summation notations I might share. You probably maybe even applied on the last example because it was so irresistible. You wanted to factor that 2 out. And you're welcome to do that anytime you want. In fact, I'm inviting you to do that. For any constant c, that can come right through the summation notation. Right? That is, in the last example, that would have been 2 times the sum of just k, right? Constants can come right out of sums. We can also break up a sum like this into if it's something plus something, we can break it up. So, you know, for example, you could do, if you have the sum of 2 to the n plus 2n, you know, that's the same as the sum of 2 to the n plus the sum of 2n. Right? That's what that's saying. And then the last one's kind of crazy. And by the way, there are a whole host of other properties I could be sharing with you, but I just thought I'd show you a couple just to give you a flavor for the fact that we can play around with sums. We can rearrange, we can do all sorts of stuff, right? The last one here, this last property, I might call the re-indexing property. Sorry, this should say plus c up here too. And that is to say, you can re-index a sum if you like, and it might, and by adjusting, it's like in the last example we had, what was it, the sum starting at k equals 4. What if you hated 4, right? You'd like, I'm not a fan of series that start with 4, k equals 4. I'd love it to start with 1. That's my favorite number, 1. How about, or whatever you like. If we made it 1, if this one goes down by 3, because it was 4, right? This k equals 4 to 7, wasn't it? So if this one goes down by 3, then we're going from 1 to, instead of 4 to 7, we're going from 1 to 4, right? Can we generate the same sum? But then instead of k squared, we have to have something else here, right? If this went down by 3, this has to go up by 3, and then verify that this is in fact, even though it looks different, is in fact the same sum as that last one we computed, isn't it? Plug in 1, 2, 3, and 4. Don't you get the exact same thing? Plug in 1, you get 4 squared, and then plug in 2, 5. Oh, yeah. All right, so that's called re-indexing, and you're welcome to do that anytime you want. Right? Sometimes it can make a sum that looks terrible look nicer. So there's a link if you want to go study other properties of summation notation. There are a dozen or more of them. Interesting things we can do to sums, just for fun. Okay. Yeah, let's try some of these properties out on these 2 examples here. So hopefully it's clear in your mind what I have up in this first. Don't look at the bottom one yet. Up at the top, I'm giving you. Remember, these are some unknown explicit rule, right? Another over here, unknown explicit rule, right? We don't know what it is. It could be crazy. N squared over n factorial plus n cubed or something, whatever. It could be anything. Who knows? Doesn't matter, though. I've told you what the sum is of this unknown sequence from n equals 10 to 100. It's 5. Yay! And over here, I've done the same thing for you over here. So can we compute, even though we have no idea what yn and xn are, this sum? Yeah, by the properties on the previous page, this is the sum 2 times yn, right, minus 5 times the sum from 10 to 100 of xn. And now both of these things are things that were given right here and right here. So we have 2 times -2 plus, excuse me, minus 5 times 5 equals -29, right? Does that make sense how these properties can work for us? All right, then the bottom one's inviting us to re-index this crazy sum. I'm just writing it here. I don't know what this evaluates to, but we could figure it out, right? Plug in 0, 1, 2, all the way up to 25. How many terms is that? 26 terms. Everyone clear on that? Okay. We could actually, like I said, we could actually get our calculator to add that up for us and see what it is, but I don't really care, actually. We're going to re-index it, though, just for fun, all right? So by k0 equals 5 down here, I mean, can you make this instead of k0? Please make it, can you make it, please, start at 5 is what I'm saying, right? Okay, so this is going to go up by 5. What goes up top? 30. And then what happens to all the k's inside the formula? Yeah, they all go down by 5, right? So up top we have k, 2 to the k minus 5, k minus 5, factorial. And then if you're ever in doubt, I mean, I kind of, you can memorize properties and things like that, but also just kind of go by feel here. Try it. If you plug in 5, 6, 7 into this formula, are you getting the same things as plugging 0, 1, 2 into this formula up here? You should be. Just verify that you're not going crazy, okay? Yeah.
This one wouldn't work, right? Because it would be 0 the first time. The first term. Like if one term in the series can't happen, what happens to the rest of them?
Can 0 not happen here? You like worried about the 0 factorial?
Yeah.
0 factorial is actually 1. So we're actually okay.
Why?
All right. Sidebar. Why is 0 factorial 1? I can give you 3 explanations. Right? The first one is I told you so. The second one is that it's the number of arrangements of 0 objects. It's not interesting, but there is one arrangement for 0 objects. Wouldn't you agree? Right? You don't like that one. I knew it. One, you might also ask about other things factorial, right? Like what about 1/2 factorial? Or what about -8 factorial, right? Wouldn't you like to know what those are?
Yeah.
Your calculator actually knows what 1/2 factorial is. Try it. And see if you can figure out what it's telling you.
How do you do factorials of like
Yeah.
fractions?
That's a good question, right? It turns out that the factorial function is an integer piece of an extension of a continuous function on the complex numbers. You might ask like what I factorial is, right? It's called the gamma function. So look up gamma function on Wikipedia, and that'll generalize it for all numbers, complex numbers, factorial, right? So that's another good explanation. It turns out that the gamma function, when you evaluate it, it's actually off by 1, but whatever. The gamma function says that it's 0. It's 1 there. Yeah. Also, you know that in the combination formula, right? Isn't it n choose 0 the same thing as n choose n, right? Maybe you've actually never computed those though by hand. When you do it, you'll have a 0 factorial in the denominator, won't you? That needs to be 1. So there are a couple ways to justify it. Was that good enough? Yeah. All right. Sorry, I've been asked that before. So someone, if you haven't already, do this one over here, and someone volunteer to read it off for me. What would you have here? We're starting at k equals -2 now. Someone read it off for him. Who's got it here? I know everyone's so excited to do it. You guys are just jumping out of your seats. You're so excited to do it. Go ahead, son.
So I count it's 23.
Got it.
And then it's k plus 2. Or 7.
There's 7. Okay.
Over 2 of k plus 2. Times k plus 2.
Yeah, and again, verify that as you start writing out the terms of this, you get the same things as when you start writing out the terms of this, right? Just to make sure you're not crazy. All right, it's kind of fun, right? Let's talk about the sum of a finite arithmetic series. But before we do, I have to tell you a story which is almost certainly false, but you've probably heard it before. Okay, have you heard the story about Gauss?
Yeah.
Okay, right. Maybe you have. Maybe you'll remember when I start telling you. But every math teacher, when we get to this part, has to sit on a stool and tell the story. Okay, so here, I'm going to sit on this stool. It's time for story time. Okay, this is the story about a young little schoolboy named Carl. Carl Friedrich Gauss, of course. Okay, and he's young, and all the other kids in his one-room schoolhouse. Because back in the old days, you're always in a one-room schoolhouse. It's also cold, I think, probably, in this story. Okay, because it always is. All right, and there's a mean teacher. Because there's always a mean teacher in the one-room schoolhouse, okay? And he's the younger of many other older kids in this one-room schoolhouse. They all lump him in. It's a one-room schoolhouse. And the mean teacher wants to keep his kids busy with some busy work. So he asks them on their slates, because everyone in the olden days also has a slate. And I don't mean like an active slate. Right? You can't ask questions during the story, sorry. Is it a good question? Okay, go ahead. He definitely walked the school uphill both ways. You're right.
Dirt floors.
And there were dirt floors, absolutely, exactly. Okay. The mean teacher asked them all to add up the numbers from 1 to 100, right? So all the kids dutifully go to work. 1 plus 2 is 3. Plus 3 is 6. Plus 4 is 10. Okay. It's going to take a while. It's good. It's keeping all the kids busy, but little Carl, he writes immediately down the sum of the first 100 numbers. And how do you do that? He comes up and slaps it onto the teacher's desk, and the teacher's just flabbergasted. So I thought I was going to be able to read the newspaper while you guys did this work. And it's absolutely correct. Do you know what the number was?
5.
What is it?
5,050.
Yeah, it's 5,050. If anyone knows has thought about this before, it's 5,050. That's what he wrote on the slate. He put it up there, and that's amazing, right? Okay, so he's this precocious man who goes on then to do amazing things, but the story's probably not true anyway. Okay, so whatever. But it's cute. Okay, it's cute still. How did he do it, though? Can someone walk us through the reasoning if you've heard of it or thought about it before? How about, who do I want to hear from? You guys are so excited about it. I love it. How about Kyle in the back? He looks like he's excited. Well, no, you didn't use a formula, actually. He thought about it another way. Ryan, see.
So 1 and 1 and 1 so it's 50 pairs.
Wait, you're saying it too quickly. I gotta track you here. So 1 plus 100 is 101, and then
Every
2.
299 is 101.
Okay, now I'm seeing it.
50 pairs, 50 times.
50 pairs of 101s. Got it. It's crystallized in my mind. That's 5,050. Okay, I'm with you, Ryan. Is that what you're going to say, too? Cool, right? Isn't Gauss awesome? Okay. Whatever. All right, so the proof of the following fact is motivated by the same kind of argument. Consider the sum first here. This is the sum of an arbitrary, not just Gauss's, right? 1 through 100. This is an arbitrary arithmetic series, right? Finite arithmetic series. The sum of the first n terms, right? Wouldn't you agree that's what I have? Nice and color-coded. Here's the first term in red. Here's the second term in blue. Wouldn't you agree? It's a little weird how I've written it, but do you agree that like this purple one here, that's the third term? A1 plus 2d, that's the definition of the third term. All the way up to the nth term in brown down at the end here, isn't that the nth term? That's the definition of the nth term. And now I'm going to write it backwards underneath, motivated somewhat by what Ryan said. And this is a little maybe harder to see, but isn't the first term the last term? We're starting the last term now and going backwards. The last term is an. The next to last term is an minus d, right? Now we're kind of going backwards down the, is that okay? All the way down to, this is a little hard to see, but that's actually the first term. That's also called a1. An minus d times n minus 1. Is that okay? Yes, Simon?
Would it be a minus?
Yeah. Is that okay? All right, and then what are we going to do? We're going to add them together, and what happens? Let's add them piece by piece. A1 plus an is what we get here. What do we get here? Blue, blue. You get a1 plus an, right? What about purples? a1 plus, oh, I see where this is going, Mr. Chase. Okay, they're all a1 plus an's. And of course, let's not forget on the left side we have 2s, don't we? Let's not forget that. How many pairs do we have? How many are there? How many pairs in this list? N of them, right? Because we added, there were n things in this list up at the top. So that's n times a1 plus an. And dividing by 2, we get our formula for the arithmetic sequence, the sum of a finite arithmetic sequence. How we evaluate a finite series, a finite arithmetic series. With n terms, right? There are two ways I like to think about this formula. You shouldn't just, it's quick to rederive too, right? If you ever need to rederive it in a dark alley. But it's easy to remember by the following, this is the way I remember it, right? I think of it as the number of terms in the series, n, times the average of the first and last term. Is that a good way to think about it? So you like that? It also reminds me of the following picture. Here's the other way, a nice way to think about it, right? I'm going to draw an arithmetic series here, like a histogram. Okay, do you agree? Like, so this is the first term, and then I'm going to add a certain amount that's always constant, right, each time. And if you were to calculate the area of this shape, what shape are we looking at, really? I mean, it's a bunch of rectangles, right? But if we were to keep doing this, what kind of overall shape do we get here? What is it? It's a trapezoid, isn't it? And so there's a formula from geometry that gives you the area of the trapezoid. And it is this one, right? It's the height of the trapezoid times the average of the bases, isn't it? So you've already encountered this formula in your life. It's the area of a trapezoid. One more picture to draw that's fun, okay? I'll do it over here for lack of space, okay? When Gauss was doing this, maybe he had this picture in his mind, right? Here's a picture of 1, 2, 3 bars of height 4, 5, etc., all the way up to a bar of height 100, right? Okay. Imagine, yes, okay. So this is a bar of height 100. Here's a bar of height 1. And if we were to compute the area of that, wouldn't that be great? We'd be done. And then here, I'm going to draw it again. Oh, sorry. Messed up. Right? All right, there's the proper picture. Okay, I'm trying to draw the sum again on top of it already, right? So sorry, I gotta get rid of the other thing too. Get rid of this too. Yeah, okay, there, that looks a little better. All right. All right, so the red and the black are meant to be the exact same. So this is 100, and this is also 1, right? And again, our goal is to find the area of the red area, or the black area equivalently. It's clear to me that the area of this entire rectangle that we've now drawn is exactly twice the area that we want. Would you agree? And the area of a rectangle is easy for me to compute. The area of the base is 100, and the area of the height of this rectangle is 101. So what's the area of the overall rectangle? 10,100, right? 1, right? divided by 2 is 5,050, right? So there's a nice visual picture of Gauss's reasoning too, right? How about a geometric series? Let's consider S, the sum of just the straight up sum of the first n terms. There it is, yay. And then I'd also like to, is that cool? Like the second term we can think of as being A1R, yeah? And the third term is A1R squared. And then I'd also like to consider RS, that is the sum we just looked at multiplied all the way through on both sides by R. Right? So every single one of these R exponents here goes up by 1. And then I'd like to, can maybe you guess? What do you think I'm going to do? Yeah, I'd like to make those things go away like the last one. So I'm going to subtract, right? And when I subtract S minus RS, all of the color-coded pairs disappear, except for A1 and A1RN, right? These guys at the beginning are at the end. So we have S minus RS on the left, and A1 and minus A1R to the n is all that's left on the right side. Factoring out an S on the left, factoring out an A1 on the right, and then dividing by 1 minus R gives us the sum formula for a finite geometric series. You don't need the proofs today if you don't want to copy them down, right? But at least get the thing in the box if you like. I like the proof though because better to understand than memorize, I say, right? These are so pretty little proofs that you really could rederive them in a few minutes off to the side if you ever forgot. Whoa. Yeah, in the video. Oh, yeah, again. Thank you. And if you want to say hi, Mom?
I'm all. My dad.
Yeah, why doesn't anyone ever say hi to Dad?
It's because we're all like on the phone.
Oh, yeah, that's right. No, wait a second. Are you good now? Are you sure? I don't want to rob you of any educational experience.
No, I'll have the video again and again and again.
That's true. You just replay it every night when you go before bed.
Turn autoplay on.
And just have a loop.
Yeah.
I love that idea. All right, let's try evaluating some sums here. Okay, so take a look at this guy. I happen to know the sum of that already. Do you know it? 42. We already did it today. Okay. Right? Okay, good. But it says use an appropriate formula. What? Wait a second. Is this arithmetic or geometric? Which one is it? We can start writing it out if you're not sure. What are the terms of this? Forget the sum for a second. What are the terms of 2k? 2k, let's see, if we plug in 1, it's 2. If we plug in 2, it's 4. If we plug in 3, it's 6. 8, 10, 12, right? What is it? What'd you say? No one's saying anything loudly. Say it like you mean it. You're scared because the video isn't. It's arithmetic, isn't it? It's 2 plus, it's with common difference 2. Okay. You can also look at the pattern here. It's linear. It's got a linear form, doesn't it? It's like 2x. It's not linear. It's not arithmetic. Okay, whatever. So what do we need for the formula for the arithmetic sum? We need to know the first term. We need to know the last term. In our case, that's term 6. We also need to know the number of terms, which is 6, right? We like 1 down here and 6 up here. If we were doing 0 to 6, how many terms is that? Like, we'd have to make n 7, even though, right? So it's not necessarily just this top limit. It's how many terms you have, okay? The first term is 2. I'm plugging 1 in. And the last term is Plug 6 in. 12. All right, so we're ready to go. Here we go. Let's see if we get 42. I'm so excited. Right? N times A1 plus AN all over 2. The moment of truth is almost upon us. Is it there? Is that 42?
Yeah.
My heart be still. Okay. All right, so we confirmed that earlier too, so that's good. What about the one down below? Which kind of series is that? If it's one that we like, it's geometric. What do we need to know in order to know the sum in the sum formula for geometric? We need to know R. Yeah, it's -3. That's in the formula. What else do we need to know? We also need to know A1 and N. That's a little bit tricky. Looking up there, do you know how many terms that is? I didn't tell you.
6.
Yeah, you could actually solve a little equation off the side if you want to. So I'll write the sum formula up here and you can evaluate it on your own. Right? It'll be the sum of the first 6 terms. So the first term times 1 minus -3 to the 6 all over 1 minus -3. So whatever that comes out to.
So I just copied
Right?
that down. Because I did
Um,
the first 2